In this video we're going to use vectors to model a projectile in Desmos. So let's say we're firing a cannonball at a speed of b meters per second at an angle of c in radians, and gravity on your planet is g meters per second squared. So we know these three, and our job is to use Desmos to model the path of this cannonball. That's our aim. So the first task is to break up this speed at this given angle. So looking at the speed, here, we need its velocity vector. Well, the velocity vector, let's break it up. So currently it's being fired at a speed of b at an angle of c. So its vertical component will be b sine c. So the vertical component will be b sine c, and its horizontal component would be b cos c. So b cos c. So now we've got our velocity vector. Now if you differentiate the velocity vector, it will then give you the acceleration vector. And remember, this is a constant because c is just an angle. When you cos an angle, it's a constant; it doesn't change. And b is also a constant. So this whole thing here is a constant. So when you differentiate it with respect to time, it would be 0. And then if you differentiate this is also a constant. It will be 0. When you're at a velocity vector, if you integrate it, it will then give you your position vector. Now when you integrate this remember, this is a constant, so when you integrate it, it will be times t. So that's where this t comes from, and this is your constant here. Well, anyway, when you integrate this, it will then give you this. Integrate this with respect to time, it will then give you this. Remember, this is just a constant. So that will then give us our position vector. And now we've got to take into account gravity. So gravity is always acting downwards. No matter where the cannonball is, gravity is always acting downwards. So let's say the cannonball is here. Gravity will act upon that cannonball. So we start out with our acceleration. So because gravity is an acceleration, over here we started out with our velocity vector, because from our given scenario we know the velocity. That's why we start with the velocity vector. When it comes to gravity is an acceleration, so we start out with acceleration as opposed to a velocity. Well, gravity is an acceleration. If you integrate acceleration, it will give you your velocity vector, and then if you integrate the velocity vector, it will then give you your position vector. So now now let's try and understand what's going on. So looking at the position of the cannonball, that's this thing and this thing. So if you think about it, if you remove gravity, let's just pretend gravity didn't exist. So there's no gravity. So imagine we're firing a cannonball with no gravity. So what that means is, at one increment of time, the cannonball will move in this manner. So it will move this much across and this much up. So it will move like this. In the absence of gravity, another second later it will move like this. Another second later, remember Newton's first law, a body will remain at rest or move at a constant velocity unless acted upon by an external force. So it will just move in a straight line. Now if you take gravity into account, what that means is this. Normally without gravity it would just move in a straight line like this. But then if you take gravity into account, let's just imagine 1 second later it moves this much, and then you've got to take gravity into account. It would move down by this much. So the cannonball would be here. And then another second later you would move this much in that direction, so we'll move like this. But don't forget, gravity is getting bigger and bigger, so that's why this magnitude is a lot bigger than this magnitude. So the cannonball will be here. Another second later, it would have moved by that same amount of vector, and then gravity will play a bigger part, because as time goes on, gravity will get the gravity will affect the position a lot more. So what I'm trying to say is that this magnitude here gets bigger and bigger as time ticks away. And then another second later, you would have moved this much of an amount, and then gravity will play a bigger part, and then, well, your cannonball will be here, and so on. That's why your trajectory will be in this manner. So if we punch it into Desmos, hang on. So combining these two vectors together, it will then give us this thing here. So now looking at the x component, it would be this plus this, which will then give you this. And then looking at the y component, it would be this plus this. That will then give you this. If you punch this into Desmos, it will then give you, if you punch this into Desmos, it will then give you this. And then add your particle, add this thing. Just change all the t's, all the t, sorry, just change all the t's to a, and then add your slider. So a, so this is your particle. This is your particle. You can see that here. Hang on. Let me move A. So you can see there, A is being moved like this. So A is our particle, our cannonball, and the path is given by this. This is our path of the cannonball. So if you change gravity, here on Earth it's 9.8. If you put on Jupiter 23 point something, you can see that the range would decrease. And then if you change it according to your planet, change gravity, change the speed, and then if you change the angle, so this is the angle here, change the angle, it will draw the path accordingly. Okay, so punch this in and play around for yourself. So now, if you're given this problem where let's say you've been put on a hill, and then you're firing a cannonball, let's say this height here is h, just make the adjustments to your Desmos. So go back to Desmos and look. So this is your x component, this is your y component. Well, you're on a hill, so let's just say you're at a height of h. Let's say an h of 50. So you just add 50, or you can add a slider, it's up to you. So add 50 accordingly, add 50. So you're on a hill at a height of 50 meters, and then now you can see that you're at a height of 50 meters, and then you can work out your range. So so let's put it back on Earth, 9.8. Close enough, yeah, okay, and then change your angle, whichever angle you want, and then you can read off the range. The range is this bit here, and so on. Well, anyway, punch this into Desmos and play around for yourself. Okay.